So interchapter C, let's see, we've done this one already. Let's mark it off. Now we're up to C.
Home stretch.
Huh?
Home stretch.
Yeah, end of next week. Okay. I think the first time I went through this one, I decided to highlight some stuff. Oh, duh. Thanks.
I was like, is it on?
Yeah, it's on. Your instructor's not here. So we've looked at at common elementary steps. This approach that we've used so far is useful, no doubt about that, but it doesn't explain what's actually happening to promote the reaction itself, other than to describe energy before and energy after and transitions of energy. What we're trying to do this time is use concepts of molecular orbital theory to explain why a reaction goes one direction and not another, or it goes mostly this direction and only a little bit the other. And we're going to start off with what's called the frontier molecular orbital theory. And this is attempting to account for the movement of electrons in these elementary steps, because that's where we're focused our attention, particularly with the curved arrows, right? They show us movement of electrons. And it can also be applied to influences of stereochemistry on the progress of a step. So, what do we mean by frontier molecular orbitals? I see them as analogous to valence electrons. These are the orbitals where the action takes place, and you can essentially ignore everything else underneath it at lower energies. These are the upper level molecular orbitals on our MO diagram. What we're looking at is actually focus your attention on differences in energies. And that's what we're referencing here in terms of energy barrier. The energy barrier is what we used to call activation energy, right? How much energy do we have to put into a collision in order for it to reach that hump and then go over the other side? So to apply it to organic chemistry, we look at the stability of transition states, right? Those activated complexes. Are they reasonably stable? And that's kind of it's relative. Stability is relative. So let's not limit our thoughts to something that's so stable that it never reacts, like diamond. So we compare transition states and say which one is more stable. If we can find a more stable transition state, then the reaction is more likely to go that direction. Right, so this red one might be one type of transition state. The blue one might be a different transition state in the way the atoms are arranged in that process. And anything we can do to lower that transition state stabilizes it and makes that elementary step more likely. So when you're looking at all those different elementary steps we've looked at so far, how do you choose which one? That was always my issue. Which one is the most likely? And that's what we're trying to get at here. Which one has the lower energy transition state would drive the reaction that direction? Okay, so these frontier molecular orbitals, are relative to only the reacting species. And if we look at, we've introduced this concept before, the HOMO and the LUMO, highest occupied molecular orbital. That is, it has electrons in it. The lowest unoccupied molecular orbital has no electrons in it. And what we want to see is, if electrons are moving, where are they going? They're moving from the highest occupied molecular orbital from one species to the lowest unoccupied molecular orbital of the other one. If there is significant overlap, if they're close to each other in energy, then that favors that particular movement of electrons. Okay. If that makes any sense. If there's little or no overlap between the HOMO and the LUMO of these reacting species, then you can pretty well eliminate that possibility, or call it forbidden if you want. So, the figure on the left is trying to show that there's proximity, closeness of the HOMO of the reactant and the LUMO of the other reactant, so that we can get electron movement from the HOMO to the LUMO without too much energy input. And where does the energy come from? Comes from the impact, right? Collision theory. They've got to collide or no reaction will occur. So the HOMO on the left is going to be a Lewis base, or a nucleophile, a contributor of electrons. And the LUMO on the right is the Lewis acid, or the electrophile. Right? The transition state, when it interacts with the HOMO interacts with the LUMO, you can visualize a bonding and an anti-bonding orbital by the combination in the transition state. Right? This is something new we didn't cover in general chemistry. Is the idea of bonding and anti-bonding. We confined that definition to actual molecules that had formed. But now we're modifying or expanding the idea so that we can include transition states. Because during a transition state, some bonds are being broken, some bonds are being formed. And we're saying that this transition state is analogous to the bonding orbital, because we've got a pair of electrons from the highest occupied molecular orbital, one reactant, going into a transition state that is a little bit lower in energy, but it's still got to make the climb to the other side in order to complete the bond. So that being said, if they're close to one another, then that transition state is not quite as low. If they're way far away, then the transition state is going to be too low to make the climb to the other side. Okay, if that makes any sense. Okay. So the HOMO has to be electron rich, the LUMO is electron poor, and we're identifying the flow of electrons from HOMO to LUMO. I don't know why this slide's in there. That's kind of superfluous. Okay, some elementary steps are the reverse of each other, but they get different names, right? The last lecture we had was on the coordination, right? Where you can form a bond by donating 2 electrons from one side and make a coordinate covalent bond. But heterolysis goes the other direction. When the bond breaks, those electrons go back to one side and the leaving group gets none of them, right? So they're I wouldn't say well, I guess you could say they're the reverse reactions. Coordination versus heterolysis. Nucleophilic addition versus nucleophilic elimination are opposite, and same thing for electrophilic addition and electrophilic elimination are opposites of each other. We could apply the frontier molecular orbital theory to each step, but it's more convenient to take advantage of these ideas. If the elementary step is allowed in the forward direction, then it would be allowed in the reverse direction. If it's forbidden in the forward direction, it's forbidden in the reverse direction. So sometimes it's easier when you're trying to determine whether a reaction will go is to say, okay, let's let the reaction go, and then say, how easy is it to go back the other direction? Right? If it's forbidden the other direction, then it never went the forward direction. I think of that as when we were trying to do ice tables and acid-base reactions. When we're trying to determine the outcome of the acid-base reaction and the pH, we would go through a step where we'd say, all right, the reaction is going all the way. And then we take the results of that and go and do the equilibrium calculation. So that's kind of analogous to what we're doing here. What if the reverse reaction has a higher activation energy? So allowed versus forbidden are relative terms, and I mentioned that earlier. It's the Einstein effect, right? It's all relative. So here we get into the idea of reversibility, microscopic. We introduced the topic of reversibility when we were discussing entropy. Right? The only way that you can get the maximum free energy from a reaction is if the reaction is reversible. And we know that no reactions are perfectly reversible. You know, we always lose something in the process. But this microscopic reversibility is ported over from those ideas so that if the reaction is the reverse of the other, it has to follow the same path in the energy diagram. It has to go through the same transition state. That's what we mean by reversibility. And since we're saying microscopic reversibility because these are elementary steps, these are not complete reactions. We've still broken things down into elementary steps that go here, 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 and they're inside the arrow for the overall reaction. The frontier molecular orbital theory focuses all of its attention on that energy barrier of the elementary step. And that's talking about kinetics. Okay. How fast does the reaction go? We haven't introduced the concept of equilibrium yet. And we probably won't get to it this semester. We get into competing elementary steps in the beginning of next term. And then it becomes a fight between which is kinetically favorable and which is that word again. Equilibrium favored. Okay, so let's take an example for this, a proton transfer. We show that the electrons from the electron-rich side, that's the HOMO, the highest occupied molecular orbital, are attacking the hydrogen in this acid, which possesses the LUMO, and we get that reaction to go. So this is just another way of thinking of it. So the reaction, we know the reaction goes, so we're saying that since it goes, then it can also go back the other direction, and the energy barrier between the two, HOMO and LUMO, must be very small. Okay, we can also visualize the HOMO of one in terms of its orbital shape and position around the the molecule. So that lone pair in that hydroxyl ion are sticking out there in that p orbital, excuse me. And the hydrogen, of course, has its s orbital, which is empty. It doesn't have any electrons in that orbital because its electron is donated to the bond. Right? So that we know that's easy one to visualize, it's empty. So when this hydroxyl approaches the hydrogen from the correct direction, right? If it came in from the other side, then you wouldn't get a reaction. We're trying to show overlap of the HOMO and the LUMO with this figure. And we say because of that, this reaction is allowed. I mean, that's not the only reason, but it's one reason because it came in from the correct direction. Remember collision theory, got to have enough energy, you got to have proper orientation for the reaction to proceed. If, on the other hand, the hydroxyl approached from this direction, there would not be substantial overlap between the HOMO and the LUMO, so that particular approach would be forbidden. And this introduces the importance of the frontier molecular orbital theory in the impact of stereochemistry on this theory. Because there are some cases where the molecules are so complex and they have steric hindrance. In other words, big groups sticking out here, getting in the way. So there's no approach from this side. It's not allowed at all. You can't get any overlap. But maybe it comes in from the other side. And that promotes that reaction that gives you a particular stereochemistry in your products. Okay, so let's look at it in terms of SN2. Right? An SN2 reaction, remember, is bimolecular. In other words, two reacting species. It's a nucleophilic attack, and it substitutes. The attacking group substitutes for the leaving group. Okay? That's what SN2 means. So we still have the same nucleophile we had in the previous slide, but now we have methyl chloride as our substrate, or our the group with the LUMO. The HOMO is the hydroxyl still. The LUMO is the methyl group, the carbon on the methyl group. It's electron deficient. Now, why is that carbon electron deficient? Because the chloride is electronegative, and it draws by induction. I remembered the word this time. It draws by induction electrons away from, actually, this is not strictly speaking induction. Induction is transferred through other groups to a position farther away. So this is simply polarity of the bond. So recognizing that the HOMO is on the hydroxyl, the nucleophile, and the LUMO is on the methyl group, carbon, then if the approach is allowed, then the reaction should be allowed. If it approaches from this side, do we get enough overlap? Well, the hydrogens are very small, right? They're not a significant steric hindrance to approaching nucleophile. All right, so we can get some overlap. Right? It's not going to come in from the other side because that wouldn't give it enough overlap, because on this side, on the middle side of the carbon, that's bonded. Right? The available LUMO is on this side of the carbon. So the approach has to be this side between all the hydrogens. And if it approaches from that direction, then we get an allowed reaction, versus approaching from the other side, that's forbidden. Okay, how about bond formation by coordination and bond breaking heterolysis steps. Okay, if we say that bromine is going to provide both electrons for the bond, and the carbon in this carbocation is relatively stable because it's a tertiary carbon. Right? So that's that carbon has the LUMO, and the HOMO is coming from the bromide. Okay, so we expect the coordination step to occur. It should be allowed. And if it does approach, what type? Okay, here's the thing about this particular molecule. It has methyl groups. I won't draw the methyls in like that. So what is the geometry of this molecule according to VSEPR?
Tertiary.
Now it's got 3 groups on the central atom. Trigonal planar.
That's,
Right, trigonal planar, right? So we can attack from this side or from the back side, either way. So what that says, and that's what this diagram is trying to show us, this positive charge is an unfilled p orbital, the LUMO, and that LUMO has 2 probability lobes sticking out on either side. We can approach from this side or from that side, and both are allowed. So what that says about stereochemistry is it could add from this side, right? It could coordinate from this side and produce, well, I don't know, just an S configuration, right? Stereochemistry, or from the other side and produce an R. So you should get a 50-50 mix of the 2. But both are allowed, which tells us that the stereochemistry could go either direction. Okay, in this heterolysis step, the bond is breaking and iodine is getting both electrons. Right, so that's 2, 4, 6, 8. Yeah, iodine now has all 8 electrons with a negative charge. And we've got a secondary carbocation left behind on this cyclohexane. All right, so in this step, since heterolysis is the reverse of coordination, is coordination allowed at that point? If we went back the other direction, yeah, it's perfectly allowed. That iodine could attack the carbon from either side, front or back. Now it may change the stereochemistry. Say if we started off with an R, let's say 1, 2, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Well, that doesn't work because this one doesn't have. That's not a chiral center at that carbon, so that argument doesn't work. So we're going to get the same product from the reverse reaction as we started with as a reactant. How about the nucleophilic addition being the reverse of nucleophilic elimination? Well, if we look at addition, we're taking a nucleophile and it's being added to the molecule. And we're forming a bond from the HOMO from the hydroxide and the electron deficient electrophile, the carbon that's attached to the carbonyl and the chloride. This carbon is not a full positive charge, but it's pretty close because the chloride is drawing electrons away and the effective electronegativity of that double bond is drawing electrons away from it also because it's attached to oxygen. Okay, so we know we have an electrophile on one side, nucleophile on the other side, HOMO this side, LUMO that side. We get an attack and that reaction is allowed. Now, the Well, that's kind of that last statement. The HOMO of the hydroxyl is a non-bonding orbital. Well, yeah, of course it is, right? Because those are lone pairs. They're not involved in bonding. So they're available, and the LUMO of the carbon on the carbonyl is an antibonding molecular orbital. Don't ask me how they know that. Let's take their word for it for now. But as we approach that carbon, right, what is an allowable overlap? Well, let's see. That carbon has unoccupied or low unoccupied molecular orbital, occupied bonding and non-bonding pair of electrons from the hydroxyl. So we get overlap, and we're able to form that bond. But that presents a problem because now carbon has exceeded its octet. And we can't do that. So that's why in the next step, okay, we're trying to show different approaches. Okay, we could come in. All right. If we look at that molecule, let's back up. If we look at the original molecule where we have carbon there, and a carbonyl here, and let's see, chlorine there, and a methyl group here. So, what is the geometry of that carbon? It's trigonal planar, right? Because it has three groups. So this trigonal planar means that it has the ability of any approaching reactant to approach from either side. That's what we're trying to show with these overlapping orbitals. It could approach from this side or from the other side to overlap with that anti-bonding pi orbital. We're using the bonding pi orbital right here. Right? There's a sigma and there's a pi. The sigma, of course, doesn't have any available. Well, actually, the sigma is, there would be less overlap with the sigma because it's spherical. The anti-bonding pi orbital has that low dumbbell effect, so the overlap is more significant. I think that's why we're getting overlap there. And the bonding is allowed either way. Now, if we look at the elimination, right, we form a product. Okay, let's see. Product is this species over here. Let's put it over this side. We have this hydroxyl, right? Then we have this chlorine, and we have this methyl group, and we have another OH, don't we? Yeah. Like that. We lost the hydrogen.
Just looking back to the next one.
Okay, hold on. The OH, okay, that one was the nucleophile. Oh, there was never a hydrogen there. I'm sorry. Right? Those electrons moved here, right? So that made this one, let's see, 2, 4, 6, 7, yeah. Negative charges there. Okay. So we've got this new species from nucleophilic addition. If we approach it from the other direction, if we say, can it go the other direction? Well, yeah, these electrons can move down here, form the double bond, which exceeds the carbon's octet. So what happens? Well, the most likely leading group is not this one anymore, it's that one. So then we can take those extra electrons that are now in this bond, give them to chlorine, and we can eliminate. And we end up with a different product. Now we end up with a carboxylic acid instead of a carbonyl chloride. But because, let's see, I'm not so sure about that. The nucleophilic addition, to be reversible, would have to lose this group, wouldn't it? If it were truly reversible, we'd have to go backwards, losing this one as the leaving group. But this one is the leaving group now. So that's kind of a, I don't know, that rubbed me the wrong way. But if you encounter an organic chemist and they insist on this microscopic reversibility and they propose this one, just kind of go with them. Because they tend to be set in their ways. Logic has less of an impact on the organic mind than it does on others. Okay, bimolecular elimination. In this case, we would, the nucleophile would attack the most vulnerable hydrogen. In this case, it's on the methyl group. And form water, which is very stable. And we would also have to take those electrons from that broken bond and put them in a pi bond, which is why we end up with ethene, or sometimes they call it ethylene. Y'all have sterilization boxes that use ethylene, or do you don't sterilize anything, do you? Okay, all right. So,
Police on the autoclave.
Yeah.
you have an autoclave?
Yeah.
Okay, I thought okay, I guess they can, autoclave works. Right. 15 pounds for 20 minutes.
15 minutes, 121.
15, okay. But an alternative way to sterilize is to package everything into gas permeable bags and put them in there and fill the environment with ethylene, and it will kill everything, but it doesn't raise the temperature. So it might be suitable for plastics. Right? If all your instruments are stainless steel, autoclave's a good way to go. We'd have to talk to our surge tech people, right through that wall. Okay, so back to the topic. In this case, if we try to use the frontier molecular orbital theory, we have to look at the process as two steps. One in which the nucleophile attacks the hydrogen and removes it, and then we get a bond break for the electrons to go into the double bond. And then because that carbon now has 1, 2, 3, 4, 5 bonds, something's got to give, and the best leaving group is the bromide. So if we're looking at it from a molecular orbital theory, we have two processes. One that forms the OH bond and breaks the hydrogen bond. So the first two arrows are the first step in the FMO theory. And then the second one is the one that forms the pi bond and breaks the, well, let's see. Okay, so what they're doing is they're saying this two-step process, this one, the whole step, and this one, you chop it right there because we broke the bond, we formed the bond and broke the bond. And then we're going to form a bond to break another bond. So that's what they're saying is this two-step process. So the formation of the bond here is between the hydroxyl and the LUMO on the hydrogen, which is fairly obvious. I don't see anything wrong with that. And then okay, now we're introducing some more stereochemistry. The anti-conformation puts the bromide away from the attacking species. And the syn conformation puts the bromide on the same side. So in order to form the double bond, you need a significant overlap between p orbitals on the methyl group where the hydrogen bond is broken, and the other one which has an available p orbital. Those have to overlap in order to form that pi bond. If, on the other hand, we put the bromide on the other side, and remember, this is a sigma bond, right? Single bond. So we can get all types of conformations. The most likely conformation is going to put the bromine in the anti-conformation. It's more stable that way. We've learned that with our stereochemistry. If we put it on the other side, it's not just the fact that the bromide is less stable being in line with that hydrogen, but it also has to do with the overlap of the orbitals. If we try to overlap orbitals in the syn conformation, it's not going to happen. Right. Okay. Is that as far as we're going? We're switching gears. Okay. So this slide only approaches the first step where you have the carbon-hydrogen bond breaking and then the double bond forming, right? We're not even talking about the bromine leaving. So how about electrophilic addition, right? So where do the attacking electrons come from? Well, the electron-rich species is the one with the pi orbit, the pi bond, right? That's the HOMO. And the electron-poor species is the hydrogen with its LUMO. And when we attack the hydrogen chloride, then something's got to give and the chlorine leaves. So that's electrophilic addition. We get a coordination plus an elimination. And okay, whenever you see an alkene with a sigma and a pi bond, that pi bond is the HOMO, because the sigma bond is at lower energy and the pi bonds are at higher energy because it's more difficult to overlap the p orbitals to make the bond. So it's at higher energy. That means it's the highest occupied molecular orbital for that species. And the LUMO for the hydrogen chloride is a sigma star orbital. We'll just take their word for it. So what if we have an electrophile elimination? That's supposedly the reverse of the electrophilic addition. Okay. I'm getting a picture here of microscopic reversibility isn't necessarily the same reaction in reverse. It's a similar concept. If we can get an electrophilic addition in one direction and an elimination in the other direction, but it doesn't have to be the same elimination as it was the addition. See what I'm saying? So if the reverse is allowed for any given elimination, then the forward addition should be allowed. That's kind of a stretch for me, but I think that's what they're getting at. So we've got a water molecule that's attacking this hydrogen. Now, why doesn't it attack the carbon, the secondary carbocation? That's my question. Let's say, for argument's sake, that it does go for that hydrogen. It could be steric hindrance. It could be any number of things. Or maybe it's a competing reaction. Maybe you do get both of them. Right? If that water attacked the carbocation, then we would form what would we form? A good leading group. Okay, let's focus on the one they're giving us here for a minute. So we attack the hydrogen. And this reaction is allowed. It forms the hydronium ion, and the electrons, the heterolysis of the bond then sends those electrons into a pi orbital. And all we're saying is that this is the reverse, the generic reverse of the earlier addition. How about rearrangements? How are they affected by the HOMO and the LUMO? Well, if we move a hydride, right, we've got to break a bond and form a bond. So, in this case, the electrons from the carbon-hydrogen bond are going to move to the carbocation, but they're going to take the hydrogen with them. How does that work? It has to be a concerted reaction. In other words, everything has to happen at the same time in order for the electrons to move and the hydrogen to move with them. Because we can't have hydrogens floating around. So, what they're saying is, and this only happens with adjacent carbons. And the reason for that is this net overlap of HOMO and LUMO. Right? The LUMO is unoccupied around that carbon because that carbon is, trigonal planar. And it has an unoccupied molecular orbital. So it looks like there is substantial overlap, and the reaction can go. Now, is it overlapping? It's actually overlapping the sigma star orbital on the hydrogen. Oops. Well, that's as far as this argument's going. So in this interchapter, we're interested in compounds with more functional groups. And we've looked at some with functional groups. Like, I think we've had the NO2 side groups. We've had the phenyl and the benzyl side groups. We're going to expand. The side groups that we're looking at now are ones that affect the suffix or the ending of the molecule's name. We've looked at some like that before, like the enes and the ines affect the ending of the name. But these are going to change the ending according to what the functional group is. So when we have a name, just to review, we have a root, we have possible prefixes, and we have the suffix. The suffix indicates the presence of a functional group other than those containing halogens, the nitro group, the NO2 group, or ethers, or the double or triple bonds. These are outside that realm. Okay. So in this case, the first thing we have to do is determine the priority of the functional group. Actually, before that, you got to see, is there a functional group that's going to affect the suffix? And then what is its priority? And we have a list of priority. Let's see, do I have that attached somewhere? Priorities. Oh, it's in a slide. Functional group priorities is in a slide. Okay. All right, so we'll look at that in a second. Then you establish that the root, the main chain or ring, and that depends on but either the length of the chain or the cycle, and whether or not there's a double or triple bond. If you have a double bond, then you have to pick the longest chain or ring that includes that double bond. And then we take the highest priority functional group, and that changes the ending of the name. If we have an alkane or an alkene or an alkyne, then we remove the E on the end before we add the suffix. And then we number the main chain of the ring. So we'll include that in our discussion too. And then we need the locator number for the highest priority functional group. We have to say where it is. Just because we found it doesn't mean that we're finished with it. We have to say where is it on the molecule. And then we can add the prefixes and their locators. All right, so here's the priority for the functional groups. This first functional group is carboxylic acid. Anytime you have this carbonyl and a hydroxyl on it, that is the carboxylic functional group. It's the highest priority. If you have that priority, then the ending of the name is always oic acid. Like, for instance, the chemical we're using today, benzoic acid. So that means we start with benzene, and we have benzoic acid. The next highest priority is acid anhydride, oic anhydride. Instead of oic acid, it's oic anhydride, because what happens in the formation of the anhydrides, we have another acid over here, and so that's a different group. And we dehydrate it. We take a water molecule, like that. That's water. And then it forms a bond right here with oxygen in the middle. That's the anhydride. They call it anhydride because we've removed an oxygen. But that's second priority. First priority is the acid. Second priority is the anhydride. Third priority is if you take instead of adding this to the end, we add some other group here, R1, and form an ester, right? Anybody have any polyester clothes? Right. The linkage in a polyester is an ester linkage, and it just goes on forever.
I use polyester urethane as like a sealant stain.
Polyester urethane. Okay, that works.
Did it have no hardwood floors?
Yeah. That's second term. The last thing we study in the second term is polymers. So, yeah, stick around for that one. Okay, so this is third priority. Fourth priority is if you add a chloride. And we're going to talk about naming esters in a subsequent section, so don't worry about that one right now. Because there are various rules that apply to esters. We used to form, when we had fatty acids, you'd have this long chain, carbon chain out here with this on the end, make our fatty acid. And we wanted to analyze for the different fatty acids that were in the extract. But we wanted to use gas chromatography. We could have used liquid chromatography, but gas chromatography is easier. These have such a high boiling point that you can't use gas chromatography. So what we do is we take our fatty acid mixture, we seal it in this ampule with methanol and acid added to it. And we form the methyl ester that has a much lower boiling point. Then we could analyze through the gas chromatograph, and we could infer based upon the esters that come out what fatty acid it belonged to. Acid chlorides. We just take benzoic, instead of oic acid, we say oil chloride, right? Instead of OIC, we say OYL chloride on the ending. And that just replaces this hydroxyl with a chloride. I would think that you could also do it with bromide too.
Oil, bromide.
Yeah, oil bromide. It's probably not as common,
Yes.
but I don't see why you couldn't do it. Now, there's also mentioned in this table of prefixes, right? If the carboxylic acid has to occupy the position of a prefix, then we would call it carboxy. Now, I'm not sure when that would be, since the carboxylic acid is the highest priority. When would carboxy be available? Right, something else would have to get in the way. And I hope that's coming, because nothing comes to mind right now. Amide. If we replace this with an NH2, say we have H like that, H like that, what else do we need there? In case we're going to react this with something? Lone pair. Yep. So that's ending is amide. So you have something and just say amide on the end. Amide is this group right here. That's amide. Next priority is nitriles. Okay, so that we get away from the acids. Now, if we have a carbon and a triple bond nitrogen, then we have a nitrile. So we don't actually change the ending. Nitrile is added to the end of the name. Aldehyde, right? That would be the next priority. That's an aldehyde. And the ending of the molecule is Al. So if we have if we had, say, C6H14, and then we took, let's see, 1, 2, 3, 4, 5, 6, and we put on the ending here, this last carbon, we put an oxygen. And of course, the hydrogen is understood. Then instead of hexane, it would be hexanal. Replace the E with the AL. Ketones. Okay. Suppose instead of doing it there, we put it here as a ketone because it has a carbon on either side of the carbonyl. So that would be change the ending to -one. Hexanone. But we have to say where it's located. So it's closer to this end, 1, 2, 3. Hexane 3 of that. Alcohol, right? We would say instead of hex, if we put an OH on the end, we still have our 6 carbons, then we would have hexanol. But we would have to say, actually before, I should have said where that the al was located. It was on the 1. This is on the 1, so this would be hexane 1-ol. Or a trivial name for that is normal hexanol. All the normals, the functional group is on the last carbon. And then the last priority is amines. So if we have, let's see. If we replace that with an N, and then we have, it depends on what's attached here, right? If it's hydrogens, then we're back up, let's see. No, that's not amide. Amine. These have to be carbons. If it's not, then we have the NH2 ending. But amines are going to have carbons on end, and that's the last priority. Now, I think, let's see, did I include that in the sample? See, because I think I included that list with the exam coming up. Yeah. Let's be sure. Yeah. So you don't have to memorize them. I put the table in the exam. And if the root is the core name of the molecule, it's an amine. If there's something else with higher priority, like if we have a carboxylic acid and an amine with it, then it becomes an amino because it's lower priority. Okay, here's some examples. This is where we really find out if we know what the rules are saying. Okay, propane 1-ol, that makes sense. Like 1, 2, 3, it could be propane 2-ol, right? Sometimes especially on old bottles of isopropanol, it'll say 2-propanol. But the proper name, the IUPAC name is propane 2-ol. In this case, it's 1-ol because the hydroxyl is attached to the ending. Ethanol, we don't have to say where the OH is located because if it's on the 2 carbon, the 2 carbon becomes the 1 carbon. Cyclohexanol, we don't have to say for that one either because all those carbons are equal. Okay, let's see. That's locator numbers. Oh, more. Amines. So for the first one, we start off with pentane, and we put the amine on the, it would have been pentanamine, but we have to say where it is. So we're saying it's pentane 3-amine. Cyclopentanamine, those all carbons are equal, so we don't have to put a locator. In the C example, we have to determine priorities. So which is a higher priority? The amine is the higher priority than the nitro. So we start numbering with the highest priority, pentanamine, and then 3 is the nitro. And I assume that we have to say that the highest priority determines the number 1 position. Right. So we're not trying to minimize numbers here. We're saying this amine says number 1 is the carbon where the amine is located. And then we number from clockwise or counterclockwise to minimize the numbers. And then the last one is we start off with hexane. And we have a chloro and we have an amine. And the amine is higher priority. So we say, all right, we're going to number from the side that gives the amine the lowest number. That's 3-amine. And then the chlorine has to be 6. 6-chlorohexane 3-amine. All right, more examples. Okay. So this one has a double bond, which means that the root has to include the double, which is not a problem here because there are no alkane attachments. So we would start off with cyclohexene cyclohexene, but the numbering previously would have put the number 1 carbon on the hexene. But since NH2 is our functional group and it changes the suffix, it starts the number 1. So the NH2, the amine is on the ending, 1-amine, and then the 2-ene tells us that we're going from there to the next carbon counterclockwise to get the double bond incorporated, the ene incorporated. So cyclohexene, cyclohex 2-ene 1-amine now needs the prefix for the chloride. And we have to put a 4, there's no option. Okay, how about the next one? We have a diene here, all right? And we have a priority, we have OH takes priority over the enes. So the ending is the lowest number for the all, 2-all. That means the 4 and the 6 designate the enes, the dienes. So it's hepta-4,6-diene 2-ol. And we would say, all right, how about, okay, here's a case where we have an ine and an ol. And since the ol is located in the middle of the molecule, we're going to minimize the numbers by starting with the number 1 carbon on the ine. Right, that makes sense. Because if we put number 1 on the ol carbon, which direction did you go from there? Right, it doesn't make sense. So we're going to start on the hept1-ine 4-ol. Okay, so here we have an amine group and we have an hydroxyl group. Hydroxyl takes priority, doesn't it? I think. Hydroxyl takes priority. So that's the end we name from, 1-ol. So it's a pentane, so we change it to pent1-ol, and then we number over to the amino group. More complicated. So we have a cyclohexane, And which one's the highest priority? The OH group. So it's hexanol. And we don't have to say one because all the carbons are equivalent. We just know that we're starting with hydroxyl, the all, and we're numbering clockwise to get the smallest numbers from there. So we'd have 2,2,2-dichloro. Let's see, let's do it this way. So we're starting with cyclohexane. Okay, so we're going to change the ending to cyclohexanol. That gets that gets the highest priority incorporated, and then we count to the right and we get 2,2-dichloro. I had to put them in the molecule with that. And then we keep going and we get a 4. Let's see. Now we get a 3 and a 4 diamino. Okay. Now, which takes priority? Well, from here we can go alphabetical, right? So amino comes before chloro. So we put this one over here and put this one here. Okay. If we have two groups that are the same priority, right? Yeah. Then we minimize the numbers. So in this first one, we have a 2,4, we have a diol. And diols. I'm trying to think if they're involved in polymerization reactions. I think some of them are. Anyway, we have a diol and we want to minimize the numbers. So we start from the right and we give a 2,4. If we started from the left, that would be 1, 2, 3, that would be 2,4. So why did we do that? I think what's happening is if we started from the left to give us 2,4-diol, that would prioritize the amino because it would be on the number 1. Right? So we have to start from the right so that the amino, we're not implying that the amino has a higher priority. Right? So we start 1, 2 on the right, and the amino has to be 5. Pentane 2,4-diol. Okay. So that second molecule has amines are higher priority than chlorides. Actually, chloride is not in our priority system, so it doesn't get a number. It's bottom of the barrel, so to speak. So we have 1, 2, 4 triamine. All right, how do we number those? Well, in this case, I think you go from the amine that gives you the next movement to an amine with the lowest number. If we put 1 on this amine on the far left, then that'd be 1, 3, 4, rather than starting with the bottom right, 1, 2, 4. Gives us a lower combination of numbers. Triamine and cyclohexane, now that we can say, all right, in that case, where are the dichloros? They're at 3 3s. Okay, here's a challenge. All right, let me draw the molecule first. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. That one. Hydroxyl. And NH2. And So. Now, okay, do we have a longest chain here? 1, 2, 3, 4, 5, 6, 7, 8, or 8. 1, 2, 3, 4, 5, 6. 1, 2, 3, 5. So this would be the longest chain, 8. Okay. But we have an E there. Okay, let me see if we get some help. Are there any functional groups that require adding a suffix? Well, we do have an all, and we have an amine. But this is higher priority. So we're going to have all as an ending. What's the longest chain that contains the highest priority functional? Oh, that contains the highest priority functional group. Okay, so now we can't say octene. We have to include these functional groups. 1, 2, 3, 4, 5, 6.
So
Hey.
it wouldn't include it even if you counted it the other way?
No, because it's got a carbon in between.
Okay.
So we've got to keep the functional groups in the root chain. Right. So this preempts the longest chain rule. Okay, so we've got if we number from the shortest end, we've got 1, 2, 3, 6. So we have 3, 6 diol so far.
It wouldn't be 1, 4.
Wait a minute. 1, 2, 3. Yeah, oh, you know what? That would be a lower number, wouldn't it? Okay, yeah, I'll go with that. 1, 4 diol. That would make this one, let's see, 1, 2, 3, 4, 5. This would be 5E. 1, 4 diol. And then this would go to the prefix. Would be amino. Yeah, amino. Would be 3 amino. X5E 1, 4 diol.
And that one comes first because it's lower.
Lower priority. Yeah, prefix, lower priority. Now let me see if I got even close with your help. Let's see, numbering it as we did there. Yeah, okay. That's correct numbering. Then keep the final E and the ene, add the die to the O. So 3. Uh-oh. Oh, I forgot that. This is 2. Let's see. This is connected at the 2. But it's a 1, 2, 3. It's a pro 2. It's not right. It's a 2 propyl. Right?
Yeah. Meth.
Oh, methyl propyl. Methyl propyl. Oh, okay. The longest one is okay. 2 methyl. Methyl 1, 2, 3. Oh, I'm not counting all my carbons. Methyl. It's 2. This is like a 2 prime. This is a 3. This is a 1. So this is your methyl attached at the 2. Methyl. This is the propyl. attached at the number 2 position. So 2-methyl propyl. 3-amino comes first because it's alphabetical, A versus M. So 3-amino, and this goes right in here. 3-amino, 2-methyl propyl, hex 5-ene 1,4 diol. Okay,
That's crazy.
I was close, right? But close only counts with hand grenades and antibombs, right? That's a tough one. Okay.
What else excited about this quiz now?
It takes more practice than I put into it. Definitely. So how do we name a molecule with more than one alkyl group bonded to the amine nitrogen? Well, by definition, if we have an amine and there's only one carbon attached to it, it's a primary amine. If we have 2, it's a secondary amine. If we have 3, it's a tertiary amine. And actually, if you have 4, it's a quaternary amine. Let's see. Determine which alkyl group attached to the N establishes the root. Okay. All right, we're not. So one of those R's, either the R prime, or the R double prime, is the root attachment. If it were a tertiary, okay, one of those is the root. Treat the other alkyl groups attached to the N as prefixes. Each of these alkyl groups is given an italic N as a locator instead of a number. So I need an example. All right. So for this molecule, the cyclohexene amine. So the amine adds to the cyclohexene at the number 1 position. Okay, I go with that. That makes the ene on that cyclohexene at the number 3 position. And it doesn't matter in this case whether you go clockwise or counterclockwise. It's the same difference. Right? Then we also have another attachment to that amine. We have a methyl group attached to the amine. But if we just say methyl cyclohexene 3-ene 1 amine, we don't know where it's attached. It could be on the ring for all we know. So we have to say where it's attached. And in this case, that methyl is attached to the N, the nitrogen. So we say N-methyl to show where it's attached. Okay, and this is a secondary amine because there are 2 R groups attached to it. The next one is a little more troublesome. We have a methoxy is not in our priority list. Right? So we go to the amine. The amine in this case is attached to the longest chain. The amine is included in the longest chain if we count 5 carbons. Okay, so it's pentane, and it's located at the 2 amine. It's located at the number 2 carbon because that gives it the lowest number. Right, so it's pentane 2 amine is the root. Then we have to say what's attached to it. Well, we have something attached to the N. The N is at the 2 position, so we're going to have some things attached to the N. We're also going to have a methoxy attached in there. So the methoxy is at the 5 position. The amine is, we already said it's at the 2 position. But what's attached to the amine? We have an ethyl group attached to the amine, and we have 2 methyl groups. one of the methyl groups is attached to the nitrogen. Actually, the ethyl group, excuse me. There's an ethyl group attached to the nitrogen. There's a methoxy attached to the number 5 carbon. We have a dimethyl.
There's a methyl at the end and a methyl at the 3, so.
That's right.
3 down
Yeah.
the.
So we have to have an N designator for one of the methyls and a 3 designator for the other methyl.
Yeah.
And then we have also an ethyl group attached to the N. Then we go alphabetical.
Yeah.
E, M, MP. MO versus MP. That's messy, isn't it? It's supposed to be logical.
I mean, it is, but it's just so many steps. that
Yeah.
you have to remember.
It's definitely a perishable skill. Okay.
Yeah, you're not doing it. All the time.
Yeah. Okay, ketones and aldehydes. Okay, the carbonyl group is any carbon double bonded to oxygen. So when we say carbonyl, we're saying in this case, for ketones, the carbonyl has 2 R groups attached to it. An aldehyde has an R group and a hydrogen attached to it. Or it could be 2 hydrogens, right? If we have 2 hydrogens attached to that carbonyl, then we have formaldehyde. If we have an R to it, then we have another, a different aldehyde. And we end it with al versus one for the ketone. So acetone would be 2 methyl groups attached to the ketone. And if we had 1, that would be acetal.
So say acetone is on like one of our quiz, will we name it propanone or acetone? Or would you think?
I'll probably take both. Yeah. It's one of those grandfathered in names.
Right.
Acetone is so common. Just like acetal instead of ethanol. Ethanol would be the proper name for acetal. And acetone, the proper name would be the propanone, right? Yeah. I think that's why they put both of them in there. Except either one. Propanone would be considered IUPAC, acetone would be trivial. Okay, so we have, in the second example, we have an acetone and an al. Which one is higher priority? The one is priority. So it's the suffix, and it occurs at the number 2 carbon because that's the end of the molecule. Well, it can't occur at the 1. There's no way. If we put it on the 1, then we've got an aldehyde. We don't have an one anymore. So ones are 2 and above. So we have the longest chain that includes the high priority is 5 carbons long. So we have a pentane 2-one, and then the hydroxy occurs at the number 4. And it has to be a prefix now. Instead of an OL at the end, now it's a hydroxy at number 4 position. How about the third one? Right. Well, we only have 1 priority there. That's the ones, but we have 2 of them. So we have a dione. Now, which direction do we label from? Doesn't matter. If you start from either side, you're going to end up with the same numbering system. That's convenient. So it's 2,4-dione from the pentane. And then we position a propyl group at the number 3. And since we don't say anything, we don't say the propyl. Actually, if we attach the propyl in the middle, then we'd have to say probably put in parentheses. Okay, the last one we have a cyclone, a cycloone. hexane 124 trione. And 1, 2, 3, 4. Yeah, we'd have to number counterclockwise in order to use the smallest numbers. Aldehyde samples. If there's only an aldehyde in there or it's higher priority than anything else, then we want the longest chain width that includes all the aldehydes. So butanal, which its trivial name used to be butyraldehyde. Butanal, if we just say butanal, it's assumed, oh, okay, we have several carbonyls in there in our examples, right? If the aldehyde is higher priority than the ketone, which I think it is, right? Aldehyde is higher priority, then we have to call the other, which would normally be a ketone, we have to call it an oxo at some position. Okay. How about that last one? A cyclic aldehyde. Yeah. So the chain that includes, that's a funny one. Carb alkane carbaldehyde. Cycloalkane carbaldehyde. Okay. Cyclopentane carbaldehyde. Okay, we're getting into deep waters.
Let's just turn the page.
I'll go for that.
It just gets worse.
Okay. This first example is fairly easy. The carboxylic acid is highest priority in any scenario. So this is going to be the longest chain that includes it is 10 carbons long. So that's decane to start with. And we have an oic acid, right, which has to be at the number 1 position. That's the only place an oic acid can be, is at the number 1. And if we start numbering from the acid end, then the ene is at carbon 2, and the oxo is at number 9. Now, why do we put an E in there? Oh, because of the double bond, right? The highest priority groups are on opposite sides. So it's an E, right? E, not a Z. Apposite, not zane. Okay. That one went pretty easy. All right, what about the last one? We have another oic acid at 1, okay? And then we have so the longest chain, including that one, is butane dioic acid. Oh, we have an oic at both ends. And since the oics can only happen, all right, here's what we're trying to do. We're trying to minimize the numbers now. Since the dioic acid, we have a carboxylic acid at both ends. Then we want a number so that we give the smallest number to the attached group. Yeah, so if we start from the right, that would give the pentyl. Yeah, 1, 2, 3, 4, 5. The pentyl is attached at number 2. And now we have to say, all right, what is its stereochemistry? So we would have to go at that number 2 carbon. If that group is toward us, then the hydrogen is back. And that's good. Because now all we have to do is priority. All right, so if we go from that number 2 carbon, and we say, all right, what's attached to it? We got a carbon, a carbon, a carbon, and a hydrogen. So we have to break a tie. So we go out from the carbon and we find oxygen. So that carboxylic acid is number one priority. Okay, so we've got this number two carbon here, number two carbon, and we've got a carboxylic acid. Yeah, it's attached to a carbon and then carboxylic acid. This one is attached to a carbon, but it's attached to another carbon. Right? And then on this side, we're attached to a carbon here, and we're attached to another carbon there. So this one was first priority. This hydrogen in the back is fourth priority. These are still tied, but this one is attached to, let's see, one attached to another carbon. These are attached to oxygens, right? And this one just keeps going to another carbon. So this one is the next priority, right? This one will be, well, two priority. And this would be three. So we're going 1, 2, 3 to the right. That's R. Okay. Yep. Now, so what would happen if this were pointed back? Say this one was pointed out and that one was pointed back. We do the same thing, and then we flip it. Right, and it'd be L. That's the easiest way to do it. Okay, nitriles. What priority is nitrile? Look at your table. It's way on down there, isn't it? Number 6, is there anything below it? Oh, gotcha. Okay, so it's higher priority than aldehydes, ketones, alcohols, and amines. Okay. My guess is it's higher priority because it has triple bond. That's the only thing that makes sense to me. Anyway, okay, so we have a situation where we have a nitrile. So that's going to be the suffix. Let's see. For the first one. So we have this hexane nitrile. So the longest chain that includes the nitrile is 6 carbons long. One, no. Hold on a second. The nitrile, here we go. The nitrile is this group. So even though it's number 1 carbon, we start counting the root from the number 2 carbon. Because if we say in this case hexane nitrile, we're saying there's 7 carbons there, but they're not. They're only 6. So that's why we start with the number 1 carbon is included in the nitrile ending. That's what I'm saying. No, now I'm wrong again. Cyclohexane, pentylohexane, hexanine nitrile. It's the highest priority. So the suffix is nitrile, yes. 6 carbons. Okay, I was wrong. We are including it. We're saying that the nitriles have to be on the end. They're always on the end. There's no other option. Okay, so it's hexane nitrile is the root. Well, the suffix and the root. Hexane nitrile, starting from the number 1 carbon. So at the number 4 position, we have a cyclopentyl. Okay, we just have to follow the convention. How about the second one? Which is higher priority here? Carbon, oh, okay, this is an oil chloride. That is very high priority. So we have to start from the other end of the molecule now, since we put a chlorine in there. We would have, I like to start with number one priority is carboxylic acid. And then this is a somewhat lower priority, but relatively high in the group as an oil chloride. So we have a 1, 2, 3, 1, 2, 3. Okay, okay, I got it. It's all clear now. Yeah, if the nitrile is a suffix, you include the carbon in the root. If the nitrile is a prefix, it's a cyano, and that is not included in the root. Okay, so we only have 3 carbons in the root. Propanoyl chloride. And the root then is added as a cyano group at the number 3 carbon. Oh. Yeah, take a deep breath. All right. Amides, as if that wasn't enough. Are we getting close to the end? No, not really. Okay. Okay, bite my lip and keep going.
We've got like 12 slides left.
Oh, and you guys got to go in a few minutes. Okay, we'll keep recording. So in this example, let's see, we have an amide. We have the amide includes the carbonyl. Yep. So the number 1 carbon is where the carbonyl is located, but that's that group that goes like this and like that. That's an amide. That's why amide is the ending. Okay, so we have an ine. If we start numbering from the carbon in the amide as 1, then we move over to number 3 is where the ine is located. Okay. Now, what's attached where? Well, we have 2 attachments on the end. One is an ethyl and one is a methyl. And that's it. N-ethyl, N-methyl. That was fairly easy. Okay, how about that next one? We have 2 carboxylic acids, so those are the endings, dioic acid, and the longest chain is 4 carbons long. The dioic, it has to occur on the terminal carbons. Okay.
I'll watch the rest of this. Thank you, Dr.
Okay. Okay, so we have butane dioic acid as our root, and then at the number 2 position, 1, 2, 3. Yeah, we would number from the right. That'd give us a lower number. And that is carbam oil. I think that's included in the prefixes for the amide. If the amide happens to be lower priority, then it's carbam oil at the number 2 position. All right. Let's see if I can name this one. See if I can name it. All right, so we have carboxylic acid, and then we have an amine, and then we have an amide or carbam oil. I bet. Yeah. So this is the carbam oil. because it's lower priority than the acid. So we have a 1, a 2, or 2. So it's ethane, ethanoic acid. Okay. And then we have at this position, I'm sorry.
Great. Or no? Would you go down?
Oh, hold on a second.
1, 2, 3.
Yeah. One, two. Yeah. Yeah, you're right. Propanoic. Because the amide is only this group, right?
Yeah.
Okay, you're right. Propanoic acid. Okay. We've taken in these 3 here. And at number 2 is 2-amine, right? 2-amine. And at 3 is carbamoyl. So it'd be 2-amine first. And 3 carbamoyl. But this is a chiral carbon. So what's the priority here? Let's see. This is in the back, so we're going to have to flip it once we find out. This is number 1 priority because it has oxygen. So that's 1. And nitrogen versus carbon. Nitrogen's next. Okay. And then this down here would be this group. This is a carbon attached to a hydrogen. This is number 3. So that would be L, but we're flipping it backwards because the hydrogen's in front, so there'll be R, correct? Yeah, R. So it'll be R. But the R is on the number 2 carbon. Let me see where I know I went wrong. Yeah, 3 carbons, right? Yeah, okay. Carbamoyl. Propanoic acid. 2-amine, 3 carbamoyl. Wait a minute. Oh, it's not given the stereochemistry. This is supposed to be, oh, this is L-asparagine, right? That's the alpha carbon. This is the carboxylic acid. That's the amino acid. And this group right here is asparagine. It makes it asparagine. But amino acids are all L. So how did we end up with R? It's got me. Unless I did priorities wrong. Carbon, that's definitely 1. This is carbon. Oh, no, no. Oh, you big dummy. Carbon, carbon, nitrogen. That's 1. Then this one is carbon to an oxygen, and this is carbon to a carbon. This is 2. This is 3. So it's 1, 2, 3 R. This is L. There we go. But L is on the number 2 carbon. So how do we designate that? Do you remember? Well, it's happy with the simpler name. But inquiring minds want to know. Textbook. So let me see. Chapter 5. One is in, and that will tell me what I need to know. Here we go. A2L. Chiral center is at the 2 carbon and it's L. That's it. So this is asparagine. All naturally occurring amino acids are L's. All naturally occurring sugars are D's. That's how I tell them apart. Okay, I'm happy now. All right, carboxylic acid derivatives on a ring structure. Okay. Include both the ring and the functional group in the root name. So a cyclic carboxylic acid takes the form of cycloalkane carboxylic acid. Cycloalkane carboxamide, cycloalkane carbonitrile. Okay. Number the carbons of the ring attached to the carbonyl containing group. Okay. So the first one would be hexane, cyclohexane carboxylic acid. And then we would number to give us the lowest value for the oxo. Okay, that's straightforward. The next one is carboxamide. So it'd be cyclopent, since there's, well, we're going to stick that one in later. Cyclopentene carboxamide at the 1, number to 2 is 2-ene. Cyclopentene carboxamide. Okay, I got that one. And the last one, cyclobutane carbonitrile. Okay, so what we're saying here is to include the suffix in the cyclic, we just prefix the suffix with carbo or carbox, carboxamide or carbonitrile or carboxylic acid. Okay. Naming esters and acid anhydrides. Okay. So in this case, I start with a carboxylic acid, and then we add the attachment, the substitution for the hydrogen on the carboxylic acid makes the ester. And whatever that alkyl group is on the ester connection, excuse me, is added into the okay. Establish the alkanoate portion of the root for the ester. Alkanoate group. So the O8 group is going to include the carboxylic acid, former carboxylic acid group. And we just changed it to O8 instead of oic. Okay. Okay, so the root is going to be butane. That first one is butanate. And then the attachment to the oxygen is a prefix, ethyl butanoate. Okay, that makes sense. The last one would be ethanoate or acetate. So it would be whatever the propyl group is attached to the ethanoic acid, be ethanoate, be propyl ethanoate. Okay. Okay. The ester is a higher priority than almost anything else. Right? So we get the all right. Okay, so that first one is going to have a 1, 2, 3, 4 carbon group, butane, and it has a hydroxyl, it has a carboxylic acid on the end, which contributes to the ester. So that's butanoate. And then we have on the butanoate, we have a 3-oxo. That's a ketone part. And then we say, with the prefix, we say what's on the end of that O8. So it's a methyl propyl group. Methyl is attached at the number 1 position of the propyl group. Okay, 1 methyl propyl, 3 oxobutanoate. Okay, that makes sense. Okay, let's go from sublime to ridiculous. In this case, our acid has a phenyl group attached to it, right? Benzyl would have a carbon in between them. This is a phenyl group because it's the ring is connected directly to the oxygen. So we have to prefix it with that phenyl. And then the rest of the molecule is 5 carbons long, pentanoate. And then we include the hydroxyls, 3,4 dihydroxy, pentanoate, and then prefix that with the attachment, phenyl. Now we have to determine what is the stereochemistry of those 2 centers, 3 and 4. Well, let's see. Highest priority. If we go to the 3 first. So we have a carbon, and hydrogen, and an oxygen. So that OH is first priority. Second priority is the one we break the tie with a double bonded oxygen and a single bonded oxygen. So that's like 3 oxygens. So we move to the right. Let's see, 1. Okay, carbon, oxygen. No. If we go to the right, we hit another carbon before we get our oxygens. Yeah. Okay, so we move to the left. The next priority is number 4 position. So we go sinister. So 3 is S. And if we look at the number 4, it's going to be S also. Yeah. Okay, so 3S, 4S, and then the rest of the description is 3,4 dihydroxy pentanoate. Okay. Now, we put the phenyl in the very front, and the 3S, 4S has to be close to where the hydroxys are. So we say 3S, 4S, then 3,4 dihydroxy. That puts those, the stereocenters and the descriptors positions for the hydroxys together. We wouldn't put 3S, 4S in the front and then phenyl. Okay. This is lovely. About, let's see, go here, oxygen, here, and there. 1, 2, 3, 4. Oh, it's 1, 5. That's 1, 2, 3. There. Right? Oxygen, and then here, and then here. Okay. So this is cyclopentyl. Cyclopentyl. And this is 1, 2, 3. Three. Propanoic. Right. Propanoate, excuse me. Propanoate. This is not going to be, this is not part, this is higher priority. So this is going to be a, you got the copy there?
Yeah, the table.
Yeah. What is this as a prefix?
Oh, let's see, it's real small. Goodness, what is it? It's nitrile?
Nitrite. Yes. Nitrite. No, wait a minute. That doesn't sound right. Let's check A, so look for priority table, bigger picture of it. Here it is. Cyano. Nitrile is the suffix, cyano is the prefix. So this would be at, let's see, 1, 2, 3. 3 cyano is in there somewhere. And this is at 1, 2, 3 hydroxy. Hydroxy, 3 hydroxy. Cyclopentyl. So cyclopentyl will come way out here at the beginning. Cyclopentyl. And then we would have C comes before H. 3 cyano, 3 hydroxy. Okay. Propanoate. But we have to say, all right, what is this one? This is at 1, 2, 3. This is at the number 3. So it's going to be 3 something. All right. So hydrogen's in the back. That's good. This is a carbon, oxygen, carbon. First priority, right? Okay. This is a carbon to another carbon. This is a carbon to a nitrogen. This is second. And this is third. So it would be sinister. 3S. Cyclopentyl, right here. 3S. 3 hydroxy. I think. Let's see what they say. S3 cyano. S3 cyano. Oh, okay. So we're trying for compactness. S3 cyano. Cyclopentyl comes first. S3 cyano. Yeah, that kind of muddies the water, doesn't it? Now why did we put it in front of the cyano? Because the hydroxyl is higher priority. 3 hydroxypropanoate. Go figure. I don't know. Compactness, maybe. Acid anhydrides. All right. For symmetric acid anhydride, in which we've taken two carboxylic acids, exactly the same, and connected them through an oxygen bridge. That's the first possibility. If that's the case, if it's symmetric, then we would use an alkanoic anhydride. So in this, let's see, is that bottom case? Yeah, the bottom case is symmetric. So that acid anhydride, well, that's a generic, so we can't do that. If it's unsymmetric, then the name of the molecule according to the general form alkanoic anhydride. Okay, we need examples. Propanoic anhydride implies that both sides of that oxygen are the same. They would be originally from propanoic acid. Okay. With the second possibility, we have ethanoic on one side and benzoic on the other side, and we do alphabetical.
So an anhydride will always have the two double.
Yes, always have the two carbonyls on either side of the oxygen. Yep. That's a dead giveaway for an anhydride. We're not going to use an anhydride. That's second term. To make aspirin. We use let's see, aspirin is acetyl salicylic acid. So we use acetic anhydride because it's more reactive. And forms a I hate it when this happens. Ester. Forms an ester more readily. Okay. Oh, that's it.